In 2019, the UK generated 323.7 gigawatt-hours of electricity, with 37% coming from renewable energy sources, like wind, solar, and biomass. Despite this surge in zero-cost energy, the expense of keeping the system stable has never been higher. In 2020, National Grid paid over £1.5 billion in balancing costs to maintain the equilibrium between load and generation. This financial strain is the primary symptom of the British electricity experiment, the 1990 decision to manage the power grid as a short-term financial market. That architecture was built for fossil fuels, and it is failing to process the variable physics of modern renewables. The UK's energy crisis stems from this systemic mismatch. A trading system designed to dispatch coal and gas lacks the coordination required to handle weather-dependent power efficiently.
National power systems are judged by the energy trilemma, the requirement to balance security of supply, affordability for the consumer, and decarbonization to reduce emissions. While the UK prioritized decarbonization, the other two pillars are fracturing. Integrating intermittent wind and solar without long-term planning has increased blackout risks and forced the consideration of load shedding. Load shedding is the deliberate shutdown of power in parts of the system to prevent a total grid collapse when demand exceeds supply. The liberalized market was engineered to optimize the dispatch of predictable fuel sources. It treats electricity as a simple commodity, ignoring the technical complexity involved in balancing a grid that relies on variable weather. Because financial trading ignores these physical constraints, the system operator must pay massive penalties to generators to adjust their output in real time. These balancing costs are added to the consumer's bill, driving up the price of electricity even when wind is abundant. To see where the system diverged, we have to look back at the era of nationalization. From 1947 to 1989, the grid was a state-run monopoly managed by the Central Electricity Generating Board, or CEGB. This was an era of centralized command. Decisions were made based on long-term systems engineering, with technical specialists prioritizing physical reliability over short-term financial returns. The CEGB integrated generation and transmission to provide base load electricity, the minimum level of power needed to meet demand 24 hours a day. They achieved this through massive, centralized coal and nuclear plants. This unified, engineering-led approach was highly efficient. By 1989, this vertically integrated arrangement had reduced the standard price of electricity to the lowest level in the country's history. The CEGB era prioritized the grid as a physical machine. Security of supply was not a byproduct of a market auction, but a strict technical mandate managed by the state. In 1990, that monolith was shattered. The UK privatized the industry, dividing the CEGB into fragmented regional electricity companies and independent generating firms. This transition introduced the power pool. Electricity was converted into a tradable commodity, where generators submitted short-term bids to sell power. Bidding structures and capital flows decoupled grid economics from the physical flow of electrons, prioritizing market-clearing prices over long-term reliability. Reforms like NETA, the new electricity trading arrangements, were introduced to drive competition. However, these mechanisms focused on short-term retail margins and largely ignored the multi-decade investment needed for the physical infrastructure. Liberalization turned the grid into a financial trading platform. While this worked for a system powered by fossil fuels, it created a structure incapable of coordinating the massive transition required for renewable energy. The market fails to handle renewables because of two specific flaws. First is the pricing flaw. The UK uses system marginal cost pricing, where the final price is set by the most expensive generator needed to meet demand, usually a gas-fired plant. Because of this rule, consumers pay a premium for gas even when zero-cost wind is abundant. The market forces all electricity to be sold at the price of that final expensive generator, decoupling the retail price from the actual cost of production. Then there is the physics flaw. The market pays for energy in megawatt hours, but it ignores grid inertia. Grid inertia is the physical momentum stored in heavy, spinning machinery that keeps the grid's frequency stable during sudden changes. Gas and coal turbines have massive rotating mass that provides this inertia naturally. Wind and solar use inverters to push static electricity onto the grid. They provide power, but they do not provide the physical shock absorbers the system needs to stay stable. As thermal plants close, the grid loses its physical stability.
To compensate, the system operator must pay billions in emergency balancing costs to simulate the inertia that used to be provided for free by the coal and gas fleet. The market values what can be traded, energy, but neglects the physical inertia the grid needs to survive. This has created a system that is both financially expensive and physically fragile. A fragmented market of private retailers cannot coordinate the physical upgrades needed to bring offshore wind power to the country's population centers. This is exacerbated by the ownership of the UK grid. Many critical energy assets are now owned by foreign governments or investment funds, which often prioritize shareholder dividends over long-term national strategic planning. To reach net zero by 2050, the UK must be able to meet a demand of 80 gigawatts. Achieving this is impossible under a market focused on short-term retail competition rather than long-term infrastructure. The British electricity experiment has failed to solve the trilemma. A fragmented market is structurally incapable of solving public good problems like national security of supply and total decarbonization. To move forward, the UK must shift the government's role from a passive market facilitator to an active statutory body, a national energy authority or future system operator. This entity would reclaim the role of technical commander, managing the grid as a smart bi-directional network rather than just a passive clearinghouse for trades. This body would use advanced metering infrastructure, or AMI, to collect high-resolution data on energy use. This allows distribution system operators, the entities responsible for local power delivery, to forecast and manage energy flows in real time. Transitioning the grid requires putting the laws of physics at the center of energy operations. We must shift from financial incentives to systems engineering. Powering the future requires replacing 20th century financial market dogma with the first principles of physical engineering. Security, affordability, and zero emissions are only possible if the grid is managed as a unified machine.